Mutex team, delivering lots and lots of emails. We've been using Go since about 2016 sometime and had a really great time with it. And one of the reasons is that it's been really easy to introspect and understand what's going on inside of Go. So today I kind of want to talk about a little thing that's been bothering me back since Go 1.9 was released, and it was a little release note that just said, Mutex is now more fair. And I was kind of like, oh, what does that mean? So I was kind of curious what the implications are, and then the other question is, why do we even care? So the reason why I think we should care is this concept of mechanical sympathy. So there's a old apocryphal story of this F1 racing driver who says that you don't have to be an engineer to be a racing driver, but you do need mechanical sympathy. And the reason that I think this is important is that when we build something and it doesn't work the way we expect, if we can reason about what's going on under the hood, we can tune things a little bit and get the best out of our engine. Go, in this case, is our engine. So there's other lower level ones where we talk about hardware, like LMAX architecture, which I think is pretty cool. But in this case, we're talking about Go and its concurrency primitives. So what was the actual problem? There was a GitHub issue posted back in 2015 about this tale of two Go routines. One holds a lock for a long time, briefly releases it, grabs the lock again. The other lock, lock B, chills out for a while, comes back, briefly acquires it, and releases it again. Now, you might assume that Go routine B, in this case, would actually acquire the lock less frequently, but still within a reasonable amount of time. Some observations have found them to be like more than 100 seconds before you even get a Go routine. And when we say holding a lock for a long time, we're talking like 100 microseconds. So clearly there's a really sort of pathological case that can happen here with mutexes. Got a little demo here. If I can find my... So this is basically the example where we have Go routine A. It's locking. It sleeps for 100 microseconds, then it unlocks again. Whereas Go routine B, and this is the one that's actually doing the measuring, is sleeps for a while, tries to grab that lock, lets us know how long it took, and we can see that we've actually gotten reasonably lucky, but we're talking upwards of 4 seconds in some cases. And you might say, don't do that. But this actually came out of a bunch of observed incidents. Kubernetes, for example, actually has a workaround for this. I believe they're doing journal transactions, and so there's Go routine in there that will periodically hold a lock for a while to do some journaling, and then release it, whereas these other things will get backed up. And I think they were seeing something in the course of hours for some locks to be acquired, which is kind of nuts. So let's dig in a little bit deeper about what's actually going on here. So Mutex basically contains two bits of data here, effectively a little state bit field, which tracks both is it locked, is there a Go routine waiting to acquire a lock, and then how many waiters are actually sitting there. So it allows the Mutex to be a little bit clever about dealing with the fact that there's actually other things there contending for this lock. The other half of this is a wait queue where Go routines that have been sitting there for a while will sort of pile up and wait for the OS to come back and wake them up again. So let's talk about locking. So the simple case is your classic compare and swap. Effectively, you try to update the state of the Mutex and say, hey, it's locked. Otherwise, you can then start spinning, and the spinning is there to avoid unnecessarily scheduling. So if a Go routine is already active, then there's a good chance that the lock will probably become free in the near future, and you can just grab that lock immediately. It doesn't have to be put back on and on the scheduler to be picked up in the future. You can just grab it straight away. So the theory behind this is that you can actually increase your sort of overall throughput even with a small amount of contention. It's worth noting here that in the case of the spinning, can it spin? Beginning processor obviously will never spin because it doesn't make any sense to do that. So the second step that happens is that if it takes too long to spin, we join a queue, and it turns out that the underlying mechanism here actually dates way back to Plan 9 and a Semaphore implementation there. Under the hook, it really relies on operating system primitives. So in the case of like Linux and I think Mac, Windows, it will use a lightweight Mutex to do this, and Mutex is effectively a way to say, hey, I want to go to sleep, and wake me up when you're ready for me to do some work. So basically that runtime semi-quiet Mutex there, that is a blocking operation. However, that just puts the thread to sleep, and then when that unblocks, the thread can go back into its loop to try to quiet the lock. But it's possible for another Go routine to come in that's already active and grab that lock before it's even possible. And this is where you can get into this state of, you go to sleep, wake up, lock's already quiet, go back to sleep, wake up again. And we kind of have our starvation issue. And the unlocking works a little bit similar here, in which when it calls sem-release, that's when it signals back to the original Go routine to say, hey, I'm done with my lock, you can wake up now, do what you got to do. And in that sort of time there before the Go routine is rescheduled, that is when another thread can come in and barge, another Go routine can barge in, grab the lock out from underneath it. I'm going to take a breath here. So barging is rather interesting because it turns out that this is sort of the accepted wisdom for dealing with locks. When dealing with high contention, barging often ends up with a much higher aggregate throughput. And the reason for this is that you can basically avoid funky stuff with the OS deciding to reschedule threads. So basically there's a cost every time you go to sleep and wake up again, and every time that happens it basically introduces overhead. And so by barging you can prevent an active thread from going to sleep. It can get on with doing its work, release the lock and move on, allowing other things to come in. So in theory this is probabilistic fair. So you have a releasing Go routine here, and it wakes up the Go routine 0, and this will try and grab that lock with a compare and swap at the same time as the barging one. Now, this is where in theory one or the other can get it. Most of the time we hope that it's writ fair, but from our little toy problem we can see that that's not always the case. Now, in this original issue, one of the speculations is that, okay, so simplest thing is we can prevent barging by simply saying, hey, in order to obtain a lock, first you need to obtain a lock, obtain a second lock, release your first lock, and then do your work. By releasing that second lock, you allow the other Go routine to actually go in, get the first one, and basically prevent barging from happening. The downside to this is this actually complicates your user code. You can implement a fair mutex that wraps this up, and so from a user point of view, sure, it looks like you're just using a mutex, but now you've got people debating, do I use a mutex, do I use a fair mutex, when's the right time to use this? And so this kind of ties back to that Go attitude of try to keep the user space simple and do the best thing where you can. So what's the goal? We want to avoid sacrificing performance, and we want to avoid imposing complexity on users. There's some sort of secondary performance things here. One of them is to continue to maintain high throughput under contention, And the other one is to minimize the overhead of unnecessarily scheduling. So this is going to happen when you have go routines constantly going to sleep, waking up again. So simple solution here is to simply, some of this starts to loop back into how the scheduler works, and what we have is a tool in the runtime to say, hey, I want to yield to the scheduler to allow another go routine to run. And by doing this, we can almost always ensure that the go routine that we've now unblocked by waking it up with sem release will immediately be scheduled and take the lock. So this actually gives us a really nice behavior in the pathological case. Downside is that now every single lock release is invoking switching of the go routine. So it's not ideal as a general solution. So the question then is what the actual solution is, and what it introduces is an adaptive mode of sorts, and this effectively puts the Mutex into a mode that we call Starvation, and what the idea of this is that it is able to detect a situation in which we're dealing with high contention, we've got go routine that can't actually acquire this lock, and we'll start simply allowing those long waiting go routines to actually start taking the lock regardless. So any new contenders coming in, they'll join the end of the queue, and that means we can guarantee that some fairness for a short amount of time. And the idea is to deal with the starvation issue as quickly as possible so that we can switch immediately back to a regular mode where we don't need to basically invoke scheduling every time that we release a lock. So starvation mode, turns out there's a little bug fix that appears out of this, which is that when we try to acquire a lock, now the Mutex actually maintains the go routine actually identifies whether it's been waiting already. And by doing that, it's able to decide whether or not, once it's woken up, does it rejoin the beginning or the end of the wait queue. Unfortunately, what was happening is our go routine B here, it would just, every time it woke up, failed to acquire the lock again, it would just enter the end of the queue again, meaning that if there were a whole bunch of other go routines up that had already entered the wait queue, you'd have to wait for all of them to be woken up first. So this, in a real situation where you're actually dealing with more than 2 go routine, could actually really have long unexpected tails. The other benefit of actually tracking this is now we can say, hey, have we been waiting longer than a certain threshold? And the threshold in this case is about 1 millisecond. Initial speculation was around that it should be about 10 milliseconds, and that was based on the garbage collector changes at the time. And it was about that point in time when this talk was happening, I think mid-2016, it was similar to a whole bunch of latency improvements on the garbage collector and Go. And about that point, they guaranteed 10 milliseconds. Whereas by the time this change was actually merged, the garbage collector guarantee was somewhere around a millisecond or lower. So it's interesting that probably informed the decision for having 1 millisecond as the starvation threshold. It's not clear. It's like one of those things you do enough spelunking through and you're not quite sure how it came to be. It's very curious how they got the what do you call it? How they benchmarked this to actually choose that number. So a little bit missing there. I'd love to know more if anyone else has any ideas. Who knows? The benefit of this upper bound though of 1 millisecond means that when you're dealing with latency, it tends to accumulate, and so the sooner you can deal with this cumulative latency, the sooner you can get back to a normal operating mode. So the major change to the actual state of the Mutex is this extra starving bit. So basically what we do now is that anytime that the go routine itself detects itself as starving, it will also mark it, the Mutex as starving for future lock attempts to be able to detect The other half of this is that any new locks getting acquired, they just simply join the end of the queue every time. They don't even bother spinning because that's a waste of time. We're just going to go into a mode where we're just pulling all the sleeping go routines off the top of the wait queue, get them done as quickly as possible, and get back to a regular mode where we don't have starvation. So the unlocking side of things, it now can see that the Mutex is in a starvation state, and it can simply hand off the scheduling directly to the next go routine. So it doesn't have to do a secondary step of unlock, lock. It just simply says, hey, schedule this next one immediately, and that way you now reduce this spinning, you reduce the contention, and again, getting out of that starvation mode as quickly as possible. Under the hood, it turns out, I tried to go into a little bit more detail here, but unfortunately I kept finding the more I dug, the more I found, and so getting back into the Semaphores, there's a whole array of stuff going on in here in how it manages its queuing. But the gist is that when you join the queue with Semaquire, it puts the go routine into a park state, which is effectively asleep. The operating system is now responsible for waking that machine thread up, and then the release step will actually flag that go routine during the waking point to actually say, hey, we've already given you the lock, you're good to go, you can skip and just go straight into your next step. So yeah, as I noted, there's quite a bit more going on under the hood with Semaphores and how the schedule interacts with that, and how the queues actually manage. So links here, I've actually got this up on, I think it's on GitHub, so lots of interesting reading to be found. But the end result of this is that we've now addressed our major problem. We've introduced a long tail, we've cut the whole long tail off, and we're in a happy place for this specific pathological case without compromising on the general behaviour. Also tried to benchmark this a little bit to show some really good examples. Turns out benchmarking is super duper hard. And the main reason I've left this here is actually Go is very convenient for doing parallel benchmarking, which is a thing that I was unaware of. This is a very simple case that actually tests contention of a mutex by using randint, because the global rand package functions are all protected by a mutex. So we can see that we haven't really gained or lost much by this change. It's all a bit of a wash for the typical case, but it only took 5 lines of Go to actually run a very simple test for this, which could test a varying number of Go routines at a time, so 1, 4, 8, etc. Lots more links here. There's a long history of this in other systems. WebKit has some really good descriptions of how they do adaptive locking. A lot of similarities. It looks like Java really continues to inform the common, beliefs and opinions in how you do locking well, and so yeah, lots to be found in there. And yeah, thanks very much. Hopefully this wasn't too much of a whirlwind, but yeah, the runtime is not scary. Anyone can get in there, and it's pretty neat. So thanks.
Were there any questions? Did you want questions?
I can attempt to answer questions.
No?
So basically, the Mutex will go the underground with operating system will do context switching, or do you want to do context switching to do spinning lock first, then do context switching?
Yeah, so the cheap sort of atomic operation is the first bet. Then try to spin for a little bit, and then give up and let the OS take care of things. So some of this ties into how Go scheduler works, which is effectively it has a bunch of threads, and Go routines are queued on those threads. And when you go into your sleep state, the thread itself it goes to sleep, and then it's up to the scheduler to decide if it wants to create other threads to handle all the other Go routines that are waiting to do stuff. I think that's the general gist as I understand it.